Good evening and welcome everyone. This is Obi-Wan Pez for N Simplex Pachinko. We are getting started and working our way back into some set theory. Which is going to be part of our work through of mathematical thinking. So if anyone is out there and has questions, feel free to drop them in. Whoa. There we go. So, we were talking about section 1.7 a while back, which is all about set theory and how do we define sets. Cantor's set theory that we were looking at was looking at the different kinds of numbers that exist in the real number set. We had left off with algebraic numbers, which were solutions to polynomial equations with rational coefficients. And can go a little bit further here. All right, so those that were non-algebraic solutions, so those that can't be solutions to polynomials with rational coefficients, are going to be called transcendental numbers. And if anybody else learned about any particular other kinds of real numbers, I guess just drop that in chat. But for now, right, our transcendental reals are going to be the next group that we talk about. So these are going to be numbers like e, which is defined as the limit as n goes to infinity of 1 plus 1 over n raised to the n, or pi, which can be defined in multiple various ways, but most commonly, lately anyway, most commonly I see it as a infinite series. So happy Pi Day, we missed it. So, right, computational formula for pi was discovered approximately in the 15th century by Madhava at the Kerala School of Astronomy and Mathematics. 16th century. And documented in Yukti Bhasa, written about 1530. So, there were several particular formulations people came up with. Pi could be 4 times the sum as I goes from 1 to infinity. Of 1 over 2i minus 1. So all odd numbers. And, oops, sorry, that's -1 raised to the I minus 1 power all over 2I minus 1. Yeah, okay. Okay, there are several other ways to define pi, but that's one of the easiest and fairly simple ways. It takes a really long time for that particular formula to yield more and more digits of pi, as it takes, 5 digits before we start getting into the fractions, which have numbers that are greater, or sorry, our number in all is less than 0.1. Sorry, wow. The magnitude of each term is less than 0.1. So we have working on a second decimal place. So that's going to be the 6th term, which starts that off. And likewise, this has more and more digits, more and more terms required to get rid of all those individual digits. To be accurate within 2 decimal places, you're going to need basically 50 terms, and 3 decimal places, you're going to need basically 500 terms. So it takes a really long time for this thing to converge. There are much better ones that are out there, but again, that's an easy one. Okay. So transcendental reals are going to be pretty much the last group that we talk about with respect to the real numbers, and so all of these are termed real. And then there is a direct mirroring of these particular numbers into what we call the imaginary numbers. And all these taken together are going to be called the complex numbers, which are going to be defined as sum a plus b times the square root of -1, where a and b are going to be some real numbers at all. And again, imaginary numbers are going to be defined by some square root of -1 multiplied by some real number. And real numbers, oops. Use the symbol with the double R. Complex numbers also likewise. Use our doubled C. All right, so okay. I'm going to throw these things into Discord real quick for saying that I am have started stream already. Whoops. Okay. Apologies for that there. Just need to make sure that the advertising was out there. And I completely and utterly neglected to do it, you know, an hour ago. Alrighty. So, in terms of the set theory that was defined inside of this particular section, alright, there's a remark here. What must be done in order to determine the solutions to a mathematical problem? So in order to prove that a set of solutions is some given t, we must prove that every solution belongs to t and must prove that every member of t is also a solution. Okay, so a set of solutions t, or a set of solutions is t, if and only if for all x belonging to t, x is a solution to our exercise, and also, wait, did I just do the second part? Oh, yeah. So that was the second part, technically. Alright, so we have every member x belonging to t for all x belonging to t. X is a solution to our exercise, and also every solution S is a member. t. Right, so the door swings both ways on this. We've got to make sure that both every x that belongs to t is a solution, and also every solution that we find S is also a member of T. So that's going to be our set of solutions. That's 1.12. So 1.13. So it says let S be the set where, defined as, within the real numbers, x squared is less than x. And let t be equal to a set of real numbers such that x is between 0 and 1. Okay. So our first claim is going to be that S and T are the same thing. So now we have to prove that that is actually true. Now, in terms of formal logic, we have to go forwards and say that, okay, all of our values that we get x, which are in S, are also in T. So if it belongs to this, then it has to belong to this as well. So given x is a member of S, this means that x squared must be less than x. So if we move this over to the other side, we get x squared minus x is less than 0. I guess in my class, I would say that this is x times x minus 1 is less than 0. And I would then prove this by saying, okay, if this were equal to 0, then we get kind of the border points where our behavior is going to change. And so for that, this is going to be x equals 0 or x minus 1 equals 0 by zero product property, which means that we got x equals 0 or x equals 1 for the number line, going from 0 to 1. Then we would want to take test values at, say, -1, 0.5 or a half, and then +2. So x times x minus 1 less than 0, is going to be either true or false for, again, -1, 1/2, and 2. So at -1, we have a -1 times -1 minus 1, which is going to be a -1 times a -2, which is equal to +2. That is not less than 0. A 1/2. Can I do that? Am I allowed? So I would say that it's okay because this is a representative value of everything within that segment. But I don't know if I'm actually allowed to do that, so let's see. Yeah, okay. Yeah. They logic their way through it, so I'm happy to do the same. Alright, so we get a 1/2 minus 1 here. It's just going to be equal to 1/2 times a -1/2, which is going to be a -1/4, less than 0. So, yes. And for 2, we've got a 2 times 2 minus 1 is equal to a 2 times 1 is going to be 2, less than 0 is false. So for this is saying that the only place that this is going to work is going to be between 0 and 1, and specifically not equal to those values. So this is saying that x must be a member of that set from 0 to 1, not inclusive, or then x is less than 1, greater than 0. All right, so proven. If x is a member of S, then x must also be a member of T. So it's between 0 and 1. Okay, then we also need to show that for all members x belonging to T, they also belong to S. Okay. Actually, that's not difficult, provided I'm thinking about this correctly. So we know that 0 is less than x is less than 1. And so since x, okay, yeah. Since x is a positive number, we're able to then multiply it on all parts of this thing. So multiply by x, we're going to end up with 0 is less than x squared is less than x. So then, again, so proven. Sometimes I get a little nervous. It's okay. Okay, so this implication on the right is showing us that for every member of T, it must also belong to S. Therefore, T is a subset of S. And over here, the exact opposite. We had all members of S are also members of T. So therefore, S is a member or subset of T. So when we take these two things together, That's when we get that s and t are going to be the same. I don't know if I want to do the next one. That's ugly. So for this one, the next example in here on 113, they say, okay, so we're going to take the exact same principle and apply it to S. It's going to be all real numbers x. Reals? Does it need to be reals? I don't think it does. So x is going to be all complex numbers, in fact, such that ax squared plus bx plus c is equal to 0. So it's going to be all solutions to the quadratic in general, and t is going to be equal to all x's within the complex numbers that are defined by either negative b plus, can do plus or minus here, shortcut it, square root b squared minus 4ac all over 2a. Absolutely. At least every one of my students. Good evening, Meglamorph. How are we doing? Mm-hmm. All right, so again, the claim here goes that s is going to be equal to t. So therefore, we have to show that s is a subset of t, and also that t is a subset of s. Not sure I want to actually do this one because it might take a while. Persistent? Interesting. I'm sorry. It seems like at the very least, perhaps, loop a doctor into that one. Is this in addition to the other one, or like instead of? Because that could also be really weird. Yeah. Well, I'm very sorry that that's... I'm sorry that that's the case. Yeah. Well, I'm very sorry about that. Like I said, I might loop a doctor in on that one. I mean, no, no. Nah, dude. It's fine. Besides, I think it's just you and me at this point. Yep, just verified. I mean, I can't empathize on that sense, and in that sense, because, yeah. Okay, so for all x belonging to S, they also belong to T. So here, this will be sufficient to prove the quadratic formula. Which actually I have done earlier in this document somewhere up here. There we go. Oh, I did it by vertex form. So I actually prefer using the vertex form of the parabola and then plugging in the individual values that we found from finding the vertex. So h is equal to negative b over 2a, and k is equal to this nastiness, c minus b squared over 4a. You plug those in and do some algebra. No, so, I mean, yes, but I don't do that. I actually start from the, I start from the function transformation form of a parabola. So I say that, okay, we're going to use this so-called ABCD in terms of our function transformation, and then say, okay, well, this B here can just be absorbed into A, and then we rename C and D to be H and K so it doesn't get in the way of the other stuff. Yeah. I found that my students kind of appreciate the quadratic formula when it comes in this form. Like, oh, by the way, if you already know where the vertex is. Now, granted, none of them use it. They just all fall back on what they remember from high school. But for some of them, it does serve them well to at least see it. All right, so top page. Ta-da! Done. And T has to be a subset of S, so for all x belonging to T, it also belongs to S. This one's going to take a little more doing, unfortunately, but whatever, it's fine. So for that one, we actually have to plug these into the formula. So this is going to be A times negative b plus or minus square root of b squared minus 4ac all over 2a parentheses squared plus b times negative b plus or minus square root b squared minus 4ac all over 2a plus c equals 0. All right, so this is going to be kind of gross, but whatever, it's fine. Well, okay. Nah, we'll do this. It's fine. A times. So here we're going to get a b squared. We're going to get a, that'll work, plus or minus in that order, twice b times square root of b squared minus 4ac. Oops. Plus, regardless of sign, the square of this thing, which is then going to just be b squared minus 4ac. All right, all over 4a squared. Plus, this one is going to be a negative b squared plus or minus b times square root of b squared minus 4ac all over 2a plus c equals 0. Way off the page. Okay, so we got a b squared here and a b squared there. So those can combine into 2b squared. A is going to divide out from the bottom, so we'll deal with that in a minute. 2b squared plus or minus 2b square root of b squared minus 4ac minus 4ac. Just seeing if I could take care of that immediately, but yeah, we'll let it ride. Over 4a. Okay, plus, it's going to be a negative b squared plus or minus b times the square root of b squared minus 4ac over 2a plus, not times, plus c equals 0. Okay, I'm going to take all this and multiply by 4a all the way across. Here that's still 0, so that's cool. This is going to get rid of its entire denominator. So 2b squared plus or minus 2b square root b squared minus 4ac minus 4ac. Here this is going to multiply the top by 2 effectively. So this is going to be a minus 2b squared. It was a positive 2, so we're good there. Plus or minus 2b square root b squared minus 4ac. Okay, plus 4ac. Awesome. Okay, so then we got some canceling out to do. So we got a 2b squared there, a negative 2b squared there, a 4ac there, negative 4ac there, and a 4ac there. Did I paint myself into a wall? Ah, okay. Because it was a negative b when we multiply them together, right? Right. So this is going to stay where it is. This, when we multiply it, becomes minus plus. I completely screwed that up. Haha. Minus plus. minus plus minus plus. Right, so then this and this end up adding up to 0 as well. 0 equals 0. Cool. So proven. Slightly tedious, but you know, one of those things where if you're actually doing formal proof, you might want to consider it. All right. Interesting. Okay. 114 lists the penny problem. So this says, given piles of pennies, we may move one coin from each pile to make a new pile. Oh, not from a pile, from each pile. There we go. Oops. All right, so then all remaining piles are one penny less than before. Okay, so we consider different orderings of the same list of sizes to be equivalent. Okay, so then the list 1, 1, 2, 5. When we take 1 off of every pile to make a new pile, that's going to be 4 pennies altogether. The 1 shrinks to 0, 1 shrinks to 0, and thus there are no piles, so we don't list them. 2 becomes 1, 5 becomes 4, and the new pile is size 4. Right, restricting our attention to lists of positive integers in non-decreasing order. Interesting, okay. So A is going to be the list that's given. B is going to be the created list afterward. A has n piles. Okay, so if A belongs to S oh, wow, okay. Skip that entirely. Let S be the set of lists of pile sizes that do not change. So if A belongs to S, then A equals B, and B has n piles of coins. Since we're creating a new pile, exactly one pile must disappear, and therefore A has exactly one pile of size 1. Therefore B must also have exactly one pile of size 1, and therefore A must have exactly one pile of size 2. And we can continue this reasoning for I from 1 to n minus 1. From A having one pile of size I, we can conclude that B must have the same pile. Therefore, A must have one pile of size I plus 1. By reasoning. Okay, so one pile, exactly one pile, all the way from 1 up to n. Cool. So this says let T be the set of lists containing one pile of each size, 1 through n. N belongs to some, or n belongs to the natural number set. Okay. Okay, so every unchanged configuration must have this form, and therefore S is a subset of T. So the sets of lists where pile sizes do not change must be a subset of the list of sets, set of lists, other way around, containing one pile of each size, due to the fact that we said that this has to be the way things work. Okay. Alright, gonna need more coffee for that. I don't know. Maybe this just seems contrived to me. I get it, though. All right, let's put the book down and think about it backwards. So now if we want to prove the other way around, that T is a subset of S, all right, we just have to think about this in terms of if we have a set of lists that goes from size 1 up through n. So given each size 1 to n, create a new pile. So 1 goes to 0, and any I goes to I minus 1. All the way up through n goes to n minus 1. And new pile is of size n. So now we've shown that this doesn't change. This must also be in T, and so therefore, nope, sorry, other way around. Must be in S. So T must be a subset of S. All right, and then taking these two things together, we now have that S must be equal to T, since they're subsets of each other. This is fine, I'm sure. Oh, right, yeah, okay. Melgomorph, I have a good one for you. This is something that came up on my last exam, or the first exam in the pre-calc class. We've got something that looks like this. Alright, that's actually supposed to be a constant, but I'm a terrible artist, so Yeah, this is just, random function. No information given about what these things are, but it's a quadratic, a linear, a constant function, and a square root. But that doesn't matter. So the entire point of this was just, okay, let's find out all of the individual properties of this particular function. So we did like, what's the domain, what's the range, all that good stuff. Last question was find all, nope, not that. Find all extrema and their types. So, students would have gone up here and said, well, this is going to be our global maximum, but it doesn't exist because it's not part of the function. So there is no global maximum for this entire function. Got that. Okay, there is no global minimum because, again, this thing's just going on forever. Next question. Are there any local mins and maxes? Apart from, like, potentially this entire thing here being called well, let's see. So all of these individual points within here to here, maybe open on this end, could be called maxima. And actually, including the last one, could be called maxima. And then everything except the last point could be potentially called a minimum on that. Or do we specifically define it so that it has to be strictly less than or strictly greater than? Because the way I think I remember it, it could potentially include. I mean, really, it's just a poor question, but I needed to come up with something that was like, legitimate and clearly defined for these students, especially. And then, do you consider these to be extrema, or does the fact that the left side of this includes something up here exclude it from being a maximum? And likewise, something just to the right of here is going to exclude this being a minimum. And like I said, I just need a better question, but the damage is done. Pretty much any student who said, like, there are none is probably going to get credit. And anybody who said, these solid points can be local, but yeah. So, like, that's the other question, right? Is if this was solid, would that be considered a local minimum? Right. Also true. Yeah. So, I mean, really, we just need better case. I need better question for that, so that's fine. Oops. Yeah, very much true. There's a little aside here about John Venn, how he was not actually the first person to use these particular diagrammatic methods, but I do know that there were Euler diagrams which were more like the set theory stuff that I have back here. We're saying like each individual nested set is, part of this particular style. Euler also included stuff that was partially in and partially out. Oops. Okay. Okay, so F is going to map some set A onto some set B. I shouldn't necessarily say onto because it doesn't necessarily mean that, but right, from A to B. Element-wise mapping. So A belonging to big A is going to make this f at A is equal to little b. B belongs to big B. Okay. So this is going to be our image. A is going to be called our domain, which I usually define, so it may not be exactly the best way of doing this, but the set of all valid inputs. B is going to be the target, oftentimes called the range. Which I say is the set of all received outputs. So it's going to be things that you actually get out. Yeah, no problem. See you on Megamorph. Hope it goes better. Thanks for stopping in. All right, so so the image of function f with domain A can be defined as the set of all f of A such that A belongs to big A. So from what I'm reading here, okay, so from what I'm reading here, we could have something that's similar to, like, let's do f, right? So f of x is equal to x squared, where domain is going to be x is all real numbers, The target appears to be that y values are also going to be real numbers, and the image is actually going to be that y is going to be greater than or equal to 0. So it seems like the image is the stuff we actually get out, and the target is the like potential space. I don't necessarily like that. Oh, yeah, there it is, right there. On the next page. Cool. Mm-hmm. Yeah. So this f is going to take reals to reals. And then the image is actually going to be only the non-negative reals. Okay. Like I said, not exactly my favorite, but that'll work. Alright, we got more definitions, remarks, all sorts of stuff like this. I'm August Forever. Hello, how's it going? Sorry, you caught me reading. I was looking at stuff that we're doing for this set theory section of this book. If you're all at all interested in dropping a question in chat, if you would like any sorts of questions answered, I can try and help out. So my name is Obi-Wan Pez. This is N-Simplex Pachinko. We are it's not too bad. I mean, everybody gets their own stages of development different, so. All right, so if we start from like kind of more basic principles, if you're looking at something that's like, oops, that's not what I wanted. So 3x plus 4x actually is a factoring problem. You don't really look at it all that much, but it is. Because what we're doing here is we're saying that these x's are basically units. So we want to say that we want to take all of the same units and try to combine them. So in this particular case, we take the x's and we're saying we're going to take 3 x's and 4 x's and combine them. How many does that make? Well, that's going to be a 3 plus 4 what's, right? 3 plus 4 x's. So basically our units come out and become a do you mean particularly quadratics? Okay, so if you get something like y equals negative 3x squared plus 5x plus 2, and you want to be able to factor this just as it is, one of the ways that you can do this is pull out a negative. So factor the negative by itself, which will leave on the inside a positive 3x squared minus 5x minus 2. Right, and then how to do the rest of it. Yeah. So it really is just, no, don't worry about it. If you've never been taught it, then, you know, it's kind of the fault of the teacher. I will say here, I do this slightly differently. I prefer doing this with the AC method, and you might have seen it before. I'm just going to hop through it because I do it, again, like I said, just slightly differently than some other people. Even the same people at my institution don't quite teach it the same. So everybody's got their own little thing. So in this particular case, we want to take a times c. So that's going to be 3 times negative 2 is going to be negative 6. And then we look at all the possible factor pairs of this thing. So 1 by 6, 2 by 3. All right, then we know that these two numbers, the negative 5 and the negative 2, come up because we're taking the two numbers in the middle that have a single x and adding them together. And that, whoa. The negative 2 comes about because we're taking those same two numbers and we're multiplying them together. Really, it's the negative 6. So the negative 6 comes about from multiplying. So here we want two numbers that are going to add up to a negative 5. Now ignore the 5 for a second. How do you get two numbers to add up to a negative value? like any negative value. How do two numbers add up to a negative value? So you could have a negative plus a negative. But what if they're opposite signs? So if you have a positive and a negative, how do you get a negative result from adding things together? Right? And what does that tell you about the size of those two numbers? So in your example, right? Yeah, we won't worry about that for a moment. So whenever you're just saying, all right, give me two numbers, add them together, and you have to have a negative result no matter what. You say, okay, well, that must mean that, again, in your case, we had the -3 and the +1. What was the relative sizes of those particular numbers? How'd you know it couldn't be the other way around? I guess is the other question. Why couldn't it have been a +3 and a -1? I'm one of those awful teachers that makes their students think. I get complaints all the time. So again, why couldn't it be the other way around? Why couldn't you have a positive? Right. So literally, if your a value is greater than 0, so you've taken, if you have a negative, you've factored it out, and you've got a positive number left over for your a. This value here, or the sign here, is going to tell you literally what is the sign of the larger factor. So the sign of the larger factor in this particular case has to be negative. There's no other way to make it work. So you come down your list and you make all your bigger numbers negative. Then you say, okay, let's go to the other one. This is what happens when you multiply your numbers together. Again, you got a -6 up here. And this is telling you whether your two signs are going to be the same or different. That's it. So if the product is positive, that's going to tell you that either both your things were positive or both your things were negative, so their signs were the same. If you get a negative there, this is telling you that your factors have to have opposite signs, different signs. So here, since this is a negative, this is telling you that you have to have opposite signs. Since the larger ones are positive, the smaller ones have to be negative. Nope. Since the larger ones are negative, the smaller ones must be positive. All right, a lot of my students want to jump to this and say, this means the smaller one's negative. That's not what that means, right? This one tells you what the sign of the larger factor. This one tells you whether they're same or different. So you have to make a small inference, but it all works pretty much the same. Okay, with that, then we take what we got up top. Y equals negative, parentheses, 3x squared. We're going to take the negative 5x, and we're going to split them into, or split it into the two factors that then add up to negative 5. So 1 and negative 6, or 2 and negative 3. Right? 2 and negative 3 is negative 1, so that doesn't work. 1 and negative 6 is going to be our negative 5 that we add up to. So we take this and we say, okay, instead of negative 5x, we're going to make a positive 1x minus 6x minus 2. Then we're going to do group factoring. So within each group, within each pair, we're going to say what's common. So in this first one, it's x. And then what's left over? 3x plus 1. What's common between these? It's a negative 2. What's left? 3x plus 1. That negative's still on the outside. We're just going to keep carrying it around. Then what's common between these two? It's a 3x plus 1. And what's left over? X minus 2. So that thing up top, the negative 3x squared plus 5x minus plus 2 factors into negative parentheses 3x plus 1, x minus 2. Yeah, I picked up tricks along the way. I shouldn't say tricks. I picked up strategies along the way. So then there's a lot of other things that you can do with this. So we can use the same strategy to do something bigger. So if we found that we had an equation, it's like 0 equals, well, that's also another thing. Let's do this. All right, so 21x squared minus 10 equals 29x. Back in the day, way back when, there was no such thing as negative values. So actually, this would have been written with a plus 10 out here, and this part would not exist. So it would have been written like this, because you can't have negative numbers. I said that just about the same time as I saw your message. So interestingly enough, right, this can be done in a couple of different ways. The way that they used to do it back in Persian Empire times. So roughly speaking, 600 to 800 years. 600 to 1100 years ago, give or take. Was that they'd actually take diagrams and make this work. So they'd say, okay, 21 can be split up into something that's 3 by 7. And these are going to be like rectangles that look like this. Usually they're squares, so it actually looks like squares. And they're even, so that they don't look all sloppy and stuff. So anyway, we would want 29 x's and 10 to fit in this exact same space. And so they try to figure out how large each thing needs to be to make it work out right. And honestly, like doing the geometry is a lot harder, especially for stuff like this. It's going to get a little nasty, but they'd make it work and it would be rather impressive. So these days we don't really do that as much because we have other methods. But our biggest one, some of my students want to take this stuff and try to factorize it just as is, or they'll move this over and be like 21x squared minus 29x equals 10, and then take out the x here, so you get 21x minus 29 equals 10. But here you're stuck. You just can't really do anything. Like, even if they were nice numbers, you're not going to get actual values here. It's really nasty, and you'd have to make it like, okay, this is 2 and this is 5. No? Okay, let's try again, and try to come up with different values. It just gets really disgusting. So we don't do that either. So these days we say, okay, bring it all over to one side. And now here, again, take your A and your C, multiply them together, you're going to get 210. Now, we know that the sign of the larger number is going to be negative. And we know that the signs have to be opposite, so we're going to get positives on this side. It's actually more than 6 factors, but whatever. This is like Wordle, honestly. We just have to try to get as close as we can, and then eventually we'll figure it out. So if we can find factors of 210, that then subtract, because their signs are opposite, their difference is going to be 29. So here, if we just do something ridiculous like 1 and 210, right, the difference between these numbers is 219, or 209, sorry. Woof. The difference between them is 209. That's way too big for 29. So we've got to get something that's much closer. So we need to pick factors which are close. So if we do, let's say, 7 and 30. So if we do 7 and 30, that'll multiply up to 210. But their difference here is only 23. So this means that the numbers are actually too close together. So we need numbers that are slightly further apart. So we've got 7. We can break out a 6. So like 6 and 35. And did it in 3. So the difference between these two numbers are now 29. Well, it gets a little weird when you start getting up into there because, again, especially in these last couple of years, people are all over the place. And, you know, you might skip a few skills here and there, but at the same time, like, you've got at least something. You're not being just carried along for no reason, right? You've done some work, you've got it, got something. So we just take that foundation and then start building on it. All right, so here, the way that I did this, again, going from 7 and -30 to 6 and -35, is that I can recognize that 7 and 30 is made up of 7 times 6 times 5. And then I just decided to switch these because I needed numbers that were slightly further apart from each other than 7 and 30. So I decided to switch these two. It could have been that I switched 5 and 7, and then I would have gotten 5 times 42. But again, 5 times 42 would have had a difference of 37, and that would be too far apart. So we need numbers that are closer. So 6 and -35 is the one. All right, so then what we do here is do the same thing. 21x squared. Now if we went the other way around, we'd actually get the same thing. So minus 35x plus 6x minus 10 equals 0. Here, common factors between 21 and 35 are going to be 7, and x squared and x are going to be x. Left over, 7 out of 21 leaves a 3. X squared, take out the x, you've got 1x left. -35, we take out the 7, we get a -5, and we've taken out the x, so that's gone. Plus, common factor here. Common factor here is going to be a 2, and then we're left with a 3x minus 5 equals 0. And again, common factor here, these are the same thing. They really need to be the same thing here. If they're not the same thing, you screwed up, go back. So 3x minus 5 multiplied by what's left, 7x plus 2 equals 0. Okay, now, in this particular case, what we want to say is we've got a product of two numbers. So we've got an a times a b. That product is equal to 0. All right, so then here, there's only one of two things that can possibly be true. If a times b is equal to 0, then either a equals 0 or b equals 0. This or is inclusive, so it also means that both of them can be 0 at the same time. In the case of quadratics like this, you can't actually do that. If the first one is 0, then the second one can't be. Because if you look at the numbers, right, there's no x value for which both of these things can be 0 at the same time. They're different from each other. All right, so then we take this and we say, oh, by this property, it's called 0 product property. Right, this is saying that 3x minus 5 must be equal to 0, or 7x plus 2 must be equal to 0. Add 5 to both sides. 3x equals 5, divide by 3. X equals 5/3. Or subtract 2 from both sides. 7x is -2. Divide by 7. X is equal to -2/7. So one of those things must be absolutely true in order to make the quadratic up top actually work. So if we start from this equation here, we could potentially plug all this in and plug in 5/3 and show that, yeah, plugging in 5/3 is going to get you the same thing on both sides. Or -2/7, plug them into both, and you show they get you the same thing. Well, I'm glad to contribute. Now, there's also really fun stuff, which could involve things like... We'll just do this one, actually. Watch. If you just do this, if you just plug y's in here and here. Oh, wait. Oh, sorry. This one's a y squared. Then what happens is we've got exactly the same setup. The middle term splits into xy's, and then the 10 stays as a y squared. The first set here still takes out a 7x, and then we'd have a 3x minus 5y left over. The second group would have a y as a common factor in addition to the 2, and then we get 3x minus 5y with 7x plus 2y left over. So even if this is like weird and a little bit complicated, turns out you can just do that. Right? Doing this in terms of the AC method is going to help out figure out pretty much any of these sorts of problems at all. It involves this pairwise grouping of factors. So you take each of the groups, factor out common factors, and then figure out if any of them have common factors. This is getting a little out of hand, especially since it doesn't actually link terribly well to the next stuff, but you know, it's all good. Just delete that for now. All right. If you have any other questions, let me know. I'm going to be sticking around for a little bit longer here, at least. And possibly moving on back to the other thing that I was working on earlier. Unless anybody interrupts me, because I'm much more willing to do other stuff than try to be motivated. So, I mean, no. Special triangles come about because of trigonometry, but that doesn't necessarily mean that, like, you absolutely sorry. I get distracted. That doesn't mean that, like, that's the only way to get them. Or the only way to figure it out. Boo. There we go. Much better. I mean, if you're trying to do, like, proving triangles are congruent to each other, then that's going to be a bit of an issue, potentially. But anyway, all these special triangles come about because of the, let's take this, let's copy it. Clipboard. Carry that on for later. Anyway, all those special triangles exist because of the relationships that happen within them. So, one, sure, cool. The 45, 45, 90. I'm not even on the line. That's terrible. I did it on the line. You'd think. There we go. So anyway, doing this, getting this 45, 45, 90 triangle. If you're talking about this in terms of the trigonometric, like, unit circle, if it's a unit circle, we could just let the radius be 1. And by geometry, we know that since we have equal angles, then our sides are going to be equal to each other. So if you don't know what those are, right, they're just x. So then here, the Pythagorean theorem, right, says that x squared plus x squared is going to be equal to 1 squared. So 2x squared is equal to 1. X squared is equal to a half. And therefore, the absolute value of x is going to be equal to the square root of 1/2. Or square root of 1 is 1 divided by the square root of 2, or root 2 over 2, or about 0.707. Right, and this is important on the unit circle because, again, you can use either values, positive or negative, it doesn't much matter. And x being both the vertical and the horizontal, it works in all 4 quadrants. Right, and if you want to do the 30, 60, 90 instead, nope, 30, right there. Okay, there. If you want to do 30, 60, 90, those 30s add up to 60. That adds up to 60. That adds up to 60. You've got an equilateral triangle. That's radius 1, that's radius 1, and this distance here is also going to be 1. Therefore, luck. I usually do the artist thing where I kind of go over it a few times. All right, so each of these sections is a half. This is 1. So then what's the horizontal? Well, let's put in x and say, well, I don't know. So here you've got now a right triangle. That's going to be 1/2 parentheses squared plus x squared equals, not plus, equals 1 squared. So again, this is 1. This is 1/4. 1/4 plus x squared equals 1. Subtract the 1/4 from both sides. You got x squared is equal to 3/4. Take the square root of both sides. That's going to be the absolute value of x is equal to square root of 3 over the square root of 4 is 2. All right, square root of 3 over 2 ends up being about 0.866. I don't remember where it goes after that, but yeah, so drawing lines straight, I mean, honestly, that's probably 20 years worth of practice. And 15 years of teaching. That's more than 20 years. Right, since I was in school. Yeah, area's fun. Have you been looking at all at, oops. You been looking at the elements at all? So it's probably available for free somewhere online. It is a 13-book excursion into geometry, which is maybe a little bit thicker than that. I would suggest just reading like the first book of the 13. Um, all 13 of them are that. Sorry, all 13 of them combined are that thick. So the very beginning of it, he starts talking about basically that he's trying to formalize geometry and turn it into a particular study. So he gives a series of definitions, he gives a series of axioms, which are things that can be taken for granted no matter what, and then the postulates, which are the things that have to be taken for granted in order for the rest of it to work. Apathum, yeah. Right, so when you're doing... All right, cool. Something like that. Right, if you're just trying to say like, regular octagon like this has a size 1, side length 1, and then you want to try to figure out the apathum, which is going to be basically an altitude to any one of the sides, and then the circumradius, so that should be it here, right? Would be the radius of a circle that is circumscribed around the thing. Right, so then this is always going to be a half. Right, so you're falling back on using right triangle trig instead of the other thing. That's interesting. So for this, oof, that's awful. Okay. Okay. So all of these, if we go with a regular octagon, for example, they're all going to break down into rectangles with right triangles, right isosceles triangles at the corners. So all these angles end up being 45 degrees. All right, so what can I do to prove that? How's this going to be useful? So these are going to be 1 over root 2. This is going to be 1 here. This is 1 over root 2. Okay, if we rewrite that, that's root 2 over 2. Okay, which means that the full width of the height and width of the octagon regular is going to have height equal to 1 plus root 2. So I'll square root of 2 over 2 on both sides plus the 1 in the middle. So it's going to get you the full height there. The apothem then is going to be root 2 over 2 plus 1/2. Or 1 plus root 2 all over 2, right? It's half the height, so that checks. All right, so there's your A. So then your R is just going to work off of this. Right, R squared is going to be equal to 1/2 squared plus 1 plus root 2 over 2 squared. So R squared equals, this is going to be 1/4. 1 plus root 2 squared. Oops. It's going to be 1 plus 2 root 2 plus 2. 3 plus 2 root 2 over 4. So here this is going to be 1 plus 3 is going to be 4 plus 2 root 2 all over 4. Leave it as is because that's equal to R squared, which then this is going to make R equals square root of 4 plus 2 root 2 all over 2. Square root top, square root bottom. Nested square roots are a little bit gross, but it works. Yeah, other angles make it a little bit harder to work with, but sometimes you have to be a little finicky. Nah. Wisdom of years more than anything. Been living inside of this subject for, like I said, long time. So if we do regular pentagon, see this is the hard one, right? So, I mean, we can come up with whatever. Right, side lengths are always 1. But then there's no real nice angles here. So, I mean, they're exactly 72 degrees, and that's nice, but, wait, no. No, they're not 72. Sorry. 108? Something like that. It's been a long time. Sorry, 72 was based on 1/5 of 360, which is not the same thing as which is not the same thing. Yeah. So that would be the 72-degree angle would be this thing here. But not the other two sides. So that's yeah. 72 leaves 108. Divide by 2. That's going to get you 54. Okay. So these here are isosceles triangles. 54-degree angles left over. So the circumradius is going to be matched up with these 54-degree angles. And you could figure out stuff using non-right triangle trig, like the law of sines and law of cosines, but nah, don't do that. So that's R, that's going to be A. What can we do with this? Alright, so R squared is equal to A squared plus a half squared in every single one of these, provided that we keep using 1 as our side length. What are we doing for a pentagon? Hang on one sec. Alright, let's see. So each side is going to get 2.5, which means this is 180 degrees straight across. So R plus A is going to be the full length across. Again, I'm not sure how this is going to help, but hey, why not? Let's see if this helps at all. Probably not. So that's our R value there. It's probably not the same as A. Can we do similar triangles at all? No, these are cut different. I mean, practically anything is possible in terms of like doing a lot of these geometries. I would suggest maybe looking up the first few sections of Euclid's Elements and try to understand what he was going for. The idea that he was going for originally was, again, formalization of mathematics, and then what are you able to build from nothing? So he said, let's have just a straight edge and a compass. And that's all we're going to use to build the entirety of mathematics. So it just takes like a straight edge. We'd use rulers these days, but the point was that it didn't have to be like marked to get a certain like distance. You just have some flat surface that is actually flat, and a compass, which will open up to whatever size you want. He did everything using like strings and sticks, basically. You know, down in the dirt, you stretch out a rope, and it makes a straight edge because you're pulling a rope taut. You can snap it to the ground, and it makes a snap line. For doing a compass, you just tie sticks to either end of the rope, hold one of them down and then draw the other one out, and it makes a circle. So Euclid's basic ideas to start with were, let's build out the entirety of mathematics using only a straight edge and a compass. Makes it a really interesting endeavor. Although I have a quote here. Somebody was not happy about it. Yeah, that one. Arthur Cayley in the mid to late 1800s said the early study of Euclid made me a hater of geometry. And John Littlewood, who, oh, maybe it's not him. Maybe it was the other one. No. Search for Truth by Bell. Yeah. Search for Truth by Eric Bell, again from the, well, this is the early 1900s, said, the cowboys have a way of trussing up a steer or a pugnacious bronco which fixes the brute so it can neither move nor think. This is the hog tie. This is what Euclid did to geometry. I don't necessarily agree, but oh yeah, there's a lot of people who didn't really like, well, math in general, but also geometry in particular. It's kind of dependent on personal taste, and there's a lot of other stuff that goes into it, but ooh, that triangle. This makes one that goes like this. This is r plus a. This is now a half. This is a right angle. So that diagonal here is going to be the square root of parentheses r plus s. Probably isn't going to do anything, but r plus a squared plus 1/2 squared. Okay, how does that help? Again, it may not, but that's that full distance there. Okay, red. That one. So then red makes a right angle like this. This is still 1 because that's the outside. This thing here, nope, this thing here is going to be half of the square root of r plus a squared plus 1/2 squared. It's half of it because it's only going out for that much. All right, and then this thing, it's probably going to be really ugly, but this is going to be the square root of 1 squared minus this thing squared. So this is going to be parentheses r plus a squared plus 1/2 squared all over 4. Again, probably just really gross and not helpful, but it's something. So law of cosines you can use on this black triangle in here with the 72 and the 54 and the 54. Law of cosines is also a generalized version of the Pythagorean theorem. So a version of the Pythagorean theorem which works on literally any of the triangles. So any. All right, so we draw a height. That's totally a height. It's totally at a right angle. And then we draw this in terms of this is our angle that we want to talk about, theta. This is going to be x. This will be, let's just call it A and B. And then all of this is C. This is going to be x. This is going to be C minus x. All right, so the cosine of theta is going to be equal to x over b. So x is equal to b cosine theta. Might be doing the wrong one. No, that works. Okay. And then over here, we say, okay, this stuff is going to be in the Pythagorean arrangement. So parentheses c minus x squared plus h squared is going to be equal to a squared. X is equal to b cosine theta. So then this is c squared minus 2 b cosine theta times c plus x squared is b squared cosine squared theta plus h. H is the sine. So the sine of theta is equal to h over b. And so h is equal to b sine theta. That means that here h squared is going to be b squared sine squared. Is equal to a squared. So then here, this actually creates an interesting thing. This is going to be b squared times cosine squared theta plus sine squared theta. Cosine squared theta plus sine squared theta is 1. This comes about from another Pythagorean triangle that you can create. So I might be able to tell you about that up there. But basically this is now just b squared. This is now c squared. So if we rewrite this, we now have a squared is equal to b squared plus c squared minus 2bc cosine theta. And my choice of where to draw the altitude, where to draw h, was arbitrary. I could have done that from any point down to any side with a right angle. So I could do that again from here down to this side at a right angle, or from this side down to here at a right angle. And in doing the same arrangement, I can get the exact same formula for all three different sides being on this side. So that this is b squared is equal to a squared plus c squared minus 2ac cosine, really it's cosine of the angle B. I labeled it incorrectly. All right, whatever. Angle B. Theta is really angle A. Yeah, right. Let me friggin'... I gotta redo it. Hang on. Little b, angle big B, side A, big angle A. Side length C is little, lowercase. That was, nope. Right, and then big C up there for the angle. Over here, again, this is now going to be cosine theta is A, big A, x over little b. Okay, this is going to be sine of A, it's h over little b. So this is going to be little b, big A. Little b, big A. All right, little a here. Little c's. That was little a. Yeah. So all this stuff is really just a matter of replacing stuff that we don't really like the look of with something that's a little bit easier to manage. Cosine big B. All right, and then also c squared is equal to a squared plus b squared minus 2ab cosine c. So again, depending on which one you actually follow, you're going to get one of these three. How you diagram this thing. But realistically, right, we don't need to prove any of the other two based on what we've got. We could just like rename the triangle and turn it around, and now you've got the other side. So not quite. You need 3 pieces of information, because here we've got 4. Right? Little ABC are all 3 sides of the triangle, and then big A is one angle. And similarly for all the others. So in order to figure out anything on this, we're going to have one of the angles. Okay, hang on, let's back up. Since we need 3 pieces of information, we need at minimum 2 of the sides, and then 1 other piece of information, whether that be one of the angles or a different side or the third side. I don't care, right? Either of those cases. So 2 sides plus 1 other piece of information gets you the law of cosines. Now, the law of sines is a little bit similar, but also slightly different. Right, of course. We set it up the same way. This is H, this is A, this is C, this is B, this is little a, little b, and then this whole thing over here is little c, but now it's broken up again into this whole x and c minus x bit. Repetition. Like I said, I've been teaching it for 15 years, so it's kind of gets drilled in there. And that doesn't mean 15 times because I teach at a 2-year school, so I teach it at least twice a year, sometimes up to 4. So with this one, in our law of sines, we're going to say that the sine of A is equal to h over b, and also the sine of B is equal to h over A, right? H over A. These are both right triangles, so this right triangle trig all works. And then here, this says that h is equal to b times the sine of big A, and h is equal to little a times the sine of big B. Well, now h and h are the same, so set them equal to each other. So b sine big A is equal to a sine big B, and then divide. So now you've got the sine of big A over A is equal to the sine of big B over B. And again, without loss of generality, we could just change it to a different one of our angles where we drop the altitude, and then we get the sine of A over A equals the sine of C over C, or the sine of B over B equals the sine of C over C. So one of the other pairs is found. And then because of that, this is going to say that, well, this is the same as the sine of big C over C. All 3 of them. Then you say, okay, so since we know that the ratio of the sine of that angle to its respective side is the same, now what we need is one pair of an angle and its respective side. Then one other piece of information. So if we looked at like the thing that we had over here, right? Our triangle inside of the pentagon. Oh man. Right, so we had something like this. This was a (72°) angle, 54, 54, and this was a 1. We know that the sine of 72 degrees divided by 1 is going to be equal to the sine of 54 degrees over whatever these were. Was that R? Oh no. Yeah, okay. Here we go. Yeah, R. So by doing, and this is the only time you're allowed to say it, doing the cross multiplication for this stuff, you end up with R equals sine of 54 degrees divided by the sine of 72 degrees, which is at least approximately. We don't have an exact value for this. It's not nice. All right, mode degrees, cool. Sine of 72 divided by the sine of 54. No, that's the other way around. Sine of 54 degrees divided by sine of 72 degrees, which realistically I could have just hit enter on that one and then flip the fraction, is about a 0.85065. So if our side lengths were all 1 centimeter, then this is going to be 0.85 centimeters. Again, approximate, but it works. And then because of that, this also says that A, this bit here, is going to be in a Pythagorean triple with R and a half. So sine of 54 degrees over the sine 72 degrees squared was equal to, was equal to 1/2 squared plus a squared. So move that over. So sine of 54 degrees over sine of 72 degrees, parentheses squared, minus 1/4 equals a squared. Take the square root of all of it. So if we square that, minus 1/4, and then take the square root of all of it. Man. Let's see. Insert parentheses raised to the 0.5 power. That'll work just the same. It's a phoenix swarm. Hey, hey. How are you doing, SDK? Hope your evening is doing very well. Good evening, Raiders. My name is Obi-Wan Pez. This is M Simplex Pachinko. We are here for we're here for some math. So Amogus Forever and I were just talking about some stuff in terms of like trying to figure out some the apothem and the oh my goodness, circumradius of certain regular polygons. I know, amazing. So basically we just drew a regular pentagon like this, draw something that gets a right angle like that. There's your A and there's your R. How do we figure this out? So it's been a little while. 1 + 1 = chicken, perhaps. So it's been a little while. We've been kicking around some law sines, law of cosine stuff, and yeah, I hope your evening was good. What did you end up doing tonight? I guess I'll also just do this thing. Hey, hey, Phasmo. Okay, so we get 0.68819 with some more stuff after that, centimeters. So, Amogus, there's your R and A for pentagons, and then you could again try to break down other shapes to do the same sort of thing. Yeah, no worries. If anyone has any math questions, let me know. I have plenty of stories as well as actual instruction. So thank you, SDK. If you're heading out for the night, hope you have a good night, and we'll see you on. Well, I'll probably be in tomorrow. I won't be streaming, but I probably can pop over if you're in. Or otherwise, I'll see people on hopefully Friday. Yeah, yep. That's this used to be coffee and now it is water, and all of that is in here somewhere. So cool. So there's a good chance I'll be on and say hi at some point. So all right. Yep, thank you for the raid. I mean, we could do all sorts of crazy stuff. Oh, missed. .3D drawing has never really been my forte, but lately I've been having to work on some of it because of the calculus classes I'm teaching. They're all like, oh yeah, you know, working on surfaces with three-dimensional shapes. I'm like, oh. Oh dear, Amogus. That's how we started our conversation in this one. So, this is hyperbolic space. This is really fascinating. It is actually a little bit on like what the art of wormholes is based on, because all the time you see it's this shape that goes like this. It's all based on, if you go to like the Museum of Science somewhere, or maybe like the Kids Museum, um, oftentimes they'll have a metal hoop that's like stuck in the floor, and it's got a pulley attached to it. And if you pull it, the thing is actually sitting in soap. And then when you pull it up, it starts like bringing a bubble up with it around you. And then immediately, almost immediately, it starts making this shape. So all the way around, it starts sucking in the middle just a little bit. It's because bubbles attempt to form the lowest surface area possible. So making a cylinder is actually very energy intensive and takes up a lot of space. So then when you pull it higher, this cylinder of soap starts pulling in the middle in order to decrease the surface area. Yeah, or very approximately. I'm not sure if it's hyperbolic or if it's something else very similar, but yeah, it's usually like that. Yeah, in the plane, it's hexagons. In three-dimensional space, it gets all crazy. So we I just talked with my Calc 2 students about something like this, wherein Euclid, the guy who created the two-dimensional geometry and did like, you know, everything. Yeah, put in a small area for turbines, yeah. And usually on the ocean, so they can pull seawater in because it's real fast to get seawater instead of having to pump in, you know, you don't want to use potable water because yeah. So anyway, we talked about hyperbolic space because Euclid had done all of these things in planar space, So he said, you know, if you draw a plane, then we can draw circles, we can draw straight lines, which allows us to say like, oh, we've got these points here, there's some cool stuff we can draw. You know, we could do all this stuff in planes. Well, what are the things that we have to take for granted if we want to say we can do stuff on planes? You know, the first one is we can draw lines between any 2 points we want. Okay, draw a straight line. Cool. What else can we do? We can draw a circle around any particular point, like that. Only, you know, more accurate. Third, we can, what was it? We can take any line that we want between 2 points and just extend it infinitely. Okay, sure. 4 is that all right angles are the same. Okay, sure, you draw a right angle here, you draw a right angle there, they're going to be the same thing. Cool. The fifth postulate is a little bit of a, what the fuck? Because what happens is, it basically says, if you draw 2 lines, and draw a third line between them, or like crossing both of them, and the sum of the angles on one side is less than 180 degrees, or less than the size of 2 right angles, then these things eventually will end up meeting on that side. So you've got all these things that are like one line. All 4 of the first 4 postulates are one line. And then the fifth postulate is like 5 lines, just all text. And I'm like, the hell? And mathematicians have been doing this exact same thing since ancient days, where they've said, okay, no, we've got to get rid of this somehow, or fix it, because you can't just say that. That's ridiculous. It's humongous. So instead, what they did was they said, okay, well, parallel lines remain the same distance apart, is basically the shortened version of that. Or lines which are not parallel, i.e., right? Like how do you even say that rigorously without actually resorting to what he said? So if you have the sum of 2 angles on one side of a transversal is less than 180 degrees, then the lines are going to meet on that side. Like, how the hell am I supposed to simplify that? And again, better mathematicians than I have been doing that for 2,000 years and have come up short. So eventually I was just like, okay. So this is Euclidean or planar geometry. So the interesting part is that if you start looking at different geometries, which do exist, then what happens is if you have the sum of 2 angles here exactly equal to 180 degrees, then in Euclidean geometry, these are going to be considered parallel. So they always remain the exact same distance apart forever in both directions. So again, Euclidean. If, on the other hand, you have 2 angles which sum up to equal to 180 degrees, but you're not on a plane, different behaviors can happen. So if you're on something with a, I believe that's positive curvature. Yeah, I think that's positive curvature. Like, you know, the planet. Then you'll notice that over time, these lines will converge. But not only will they converge on one side, but they'll also do it on the other. And they meet at antipodal points. So on a sphere, this ends up being like these two curves. So they go around our sphere. They're going to hit at 2 points, one here and one here. They're antipodes of each other, so they're on exactly opposite sides of a sphere. And so this is spherical geometry. This is the stuff that lets GPS work and, like, you know, all this other stuff. So here's the thing. Everybody knew that the Earth was round, and everybody knew approximately how all this worked. Going back to Eratosthenes in like 300 BCE or something like that. Eratosthenes, back in Greece, he was the first one to figure out how big the Earth was. He got it to within 2%, so not too bad. He went to someplace in Greece where he lived, and he found a big well. And on the solstice, summer solstice, he looked down the well and found out that the sun was pointing straight down the well. Or no, it was at a particular angle, whatever. And then over in Alexandria, in Egypt, he did the same thing. And he knew what the length was to get from one place to the next. So from Greece to Egypt was like a known 500 kilometers or something like that. And then he said, oh, well, I know what the angle is because I know what the angles between the actual like sun and the earth. Yeah, I know the angles between the sun and the earth. Two curbs. Welcome, good evening. I don't have a queue system set up, so feel free to ask the question. I will get back to you. So he said, okay, if I know what the angle is here, and I know that this is 500 kilometers to get from Greece to Egypt in these particular locations, again, this give or take, then I can figure out what the whole circle is, assuming that it is actually a circle, or very nearly a circle. And when he did that, he found out that the Earth was about 21,000 miles, I think, actually. Yeah, around 21,000 miles in circumference. And again, he actually did pretty well. He was within about 2%. So then, Al-Jayani, in and around 1200 CE, figured out that he could do actual algebra on the sphere and be able to come up with the entire field of spherical geometry. So he formalized everything in much the same way that Euclid did planar geometry. That way. Al-Jayani did spherical geometry. And then it wasn't until the 1800s when Nikolai Lobachevsky, Russian mathematician, and Bolyai, who was a Hungarian mathematician. Of course, I forgot his name. Janos. So Janos Bolyai and Nikolai Lobachevsky both came up with the field of hyperbolic geometry. And in hyperbolic geometry, unlike the other two, like spherical or planar, what happened was that from a specific line that has, again, angles on one side summing up to exactly 180 degrees, our lines actually start diverging. So they curve away from each other. It's only locally that they look parallel to each other. Once you start going away from there, they diverge. So that's where we get this thing. And again, they started doing the formalized treatment the same way that Euclid did with planar geometry and Al-Jayani did with spherical geometry. So, I mean, it took until the 1800s to actually get it. Okay, so two curves. Suppose you have a bunch of points from a distribution you assume is Poisson. You want to transform these points such that the mean and variance are 1. Okay, so you're normalizing it, essentially. Poisson distribution. Hey, Rennie Guppy, how you doing? Game 3 question. I don't remember the exact question, but 4 pages, huh? Whoa. That's always fun. Never tedious. Oh, man. Oops. Didn't mean to do that. No. Okay, there we go. I'm okay, I promise. Poisson x mu is equal to e to the negative mu times mu to the x over x factorial. Okay. Prove a set is bounded using the Euclidean norm. Okay. All right, so two curves. This is what I'm reading. So the Poisson distribution is going to be P of x mu, where we get e to the negative mu times mu to the x over x factorial. X is going to be the number of occurrences of this thing happening. Mu is going to be both the expected value and variance. Maybe? According to the thing I read. Okay. So if we want to normalize mu to become 1. Or at least mu to become 1. So like the mu terms are going to become 1. That sounds right. This is the distribution anyway. You're looking at a full data set. Yeah. So normally when we do this in like vector calculus, that's the sort of thing we do, is we say like, you've got a vector which is equal to ax hat plus by hat. So it's like some particular location like that. And then you want to normalize it so that the distance of it is 1. So that the norm of v is going to be divided. Yeah. Hopefully. Anyway, good luck. So you get like ax hat plus b y hat over norm of v. For us, x hat plus by hat over square root a squared plus b squared. All right. Does anyone have any other questions? Feel free to ask. Doesn't have to be strictly content related if you want to talk about something else. Alright. I think with that, it is now midnight, and probably going to head out. So, we can check out who's on tonight. Suspect Jason Charles Miller is on. Anybody who doesn't know JCM, he is a content creator, musician, and other awesome all-around kind of person. Oh, he's not on tonight. I'm putting my foot in my mouth there. Okay, cool. Cool. So, you know what? Let's go see. Let's go see. Adriosa. Haven't been over to hers in a while, and she's been taking some time off, so we're gonna go see her tonight. I totally went to the wrong page. Cool. Stream manager. So let's load up for a raid. She is playing Elden Ring tonight. Be prepared for lots of swearing. So just, you know, heads up. All right, so this Friday, 2 days from now, we are going to be coming back for more Final Fantasy VII remix, redux, whatever it is, remake. There we go. Final Fantasy VII remake. Things are getting good. We're just getting into the, let's see, we're still in town in sector 7, just before we start the second job. So if anybody has played the original Final Fantasy VII or the remake, yeah, the second job is coming up next. So probably hit that. And I've been running around town trying to do the odd jobs here and there to get more money and whatnot. So, you know. Oh, and see what other fun stuff they've put in the game to make a completionist like me spend hours and hours and hours on it. So I will see you all on Friday. If not, next Wednesday for more math stuff. We're probably going to start again back with the Mathematical Thinking by D'Angelo and looking at more stuff. Where were we? Down with the functions section. So we're going to define functions a little more strictly and whatnot. And get into some of that stuff. So, thank you very much. This is Obi-Wan Pez for N Simplex Pachinko. We are going to head out tonight. Go see Adriosa. Those who don't know her, Adriana